There are many classifications of facade types in relation to water management, ranging from perfect barriers, such as precast and curtain wall facades, rainscreens, such as cladding with ventilated cavity or insulated render systems with drain cavities. And there are endless combinations, such as unitized curtain wall facades and sandwich panels covered in rainscreen cladding. But the most useful classification was coined by Joseph Stiebrecht, who believes that there are only two types of facades: those that leak and those that will leak. I think he was saying this in context of windows, but I'm going with facades anyway. And that brings us to today's mission. How do we keep facades in that second category, the will leak, rather than the currently leaking, for as long as humanly possible? Now, our very own building regulations, part C, that is site preparation and resistance to contaminants and moisture, for those keeping score at home, has some pretty clear expectations. It says walls shouldn't leak, shouldn't promote condensation, and definitely shouldn't turn into mold farms. A fairly reasonable request. The regulations even give us some practical guidance on how to design external walls to keep water on the outside, where it belongs. Let's dive into these considerations using real examples from our Facade Intelligence platform case studies, because nothing beats learning from actual buildings. Now here is where the things get interesting. Building regulations appear to give designers a free pass to use external insulated render systems without cavities. No mandate for a water-resistive barrier membrane either. So technically, you can slap insulation directly onto masonry or concrete wall, throw some render over the top and call it a day. No cavity, no render membrane, nothing. This is what Professor Straub would call a perfect barrier wall. Basically, you're betting the farm on that thin layer of external render being absolutely watertight forever. Now, the regulations do mention water-resistive barriers, but only when they are talking about stud walls. Here they call it a breather membrane by saying it has to be vapor open, but it should resist the passage of liquid water and it has to be installed on the side of the cavity. The diagram even shows a vapor control layer on the inside of the stud wall, though interestingly, they don't actually specify that it needs to be vapor closed. These two diagrams do not show the insulation within the cavity between the breather membrane and the cladding, but there is a little asterisk at the bottom that's easy to miss. For light steel frame construction, they require external insulation to be placed over the frame within the cavity. And that tiny asterisk is how we end up with the most popular facade system in the UK, the rainscreen cladding wall. You've got your thin gauge galvanized steel frame, we call it LSFS or just SFS if you want to sound cool, wrapped in sheathing board that acts as your air barrier, then covered with weather-resistant breather membrane, topped with external insulation, and finally separated from your cladding by a drained and vented cavity. Now you might think, hang on, the building regs seem to suggest I could just stick some insulated render straight onto the wall and call it done. No cavity needed. And you would be technically correct, but here's where the reality clashes into regulations. The warranty providers, the people who actually pick up the bill when the building starts leaking, they take a very different view. NHBC and their colleagues from LABC have seen this movie before and they didn't like how it ended. So they have stepped in with some clarification. Remember Professor Straub's second D, drainage? Well, NHBC has made it mandatory. They now require external insulated render system to have a minimum 25mm drain cavity between the insulation and the sheeting board with breather membrane, if the stud wall is used as a backing structure. But here's where things get tricky. This clever cavity solution creates its own problem. What happens when you've got cavity sitting right above a window? It is like having a water collection system positioned exactly where you don't want water to go. As a solution, we go back to the Professor Straub's first D, deflection. But this time we are doing deflection inside the wall where no one can see it. This is done by a channel above the opening installed at the angle to the head reveal, deflecting the water away from the window, directing it down to drainage holes at the bottom of the cavity at the ground level, doing exactly what a traditional drip edge would do, but hidden within the facade assembly. So you can see now that the deflection strategy is used not only on the surface of the facade, but within the build-up, not visible from the outside at all. Another example of such invisible deflection strategy could be seen in masonry veneer walls. Approved document C is quite specific here. They want cavity trays with a minimum 150mm drop from the inner leaf to the outer leaf, all leading to those crucial weep holes in brick cladding. It's like building a series of invisible gutters inside. The spacing requirements are quite specific. Weep holes every 900mm maximum, with minimum 2 weep holes above each window where the cavity tray doesn't continue past the lintel. And warranty providers absolutely scrutinize these details during inspections. They are checking for 1 weep hole every 3rd brick at the slab level and ensuring at least 2 per window opening. There is a reason for their vigilance, because when weep holes aren't properly spaced or cavity trays lack sufficient fall from inner to out, problems develop quickly. The real trouble starts when mortar debris fills the gap between the cavity tray and the brick, essentially creating a dam where you need drainage. What happens next is predictable. Water ponds behind the brickwork and the brick starts its inevitable decline, turning gray and developing that horrible moss growth on the surface. Now, this is actually an optimistic scenario. At least the water is still making its way on the outside. Once the water finds its way on the building's interior, you are facing complete facade removal and reconstruction. Now, to be fair to this particular building, the weep holes were installed, just not quite where they should be. They are positioned 4 courses above the cavity trays, and in some locations they are missing entirely. The result is remarkably telling. The clear line of moss and mold growth creates a perfect visual map showing exactly where the cavity trays are located and where weep holes are absent. You can literally read the facade drainage strategy just by looking at the staining patterns. The reason for the stains is that brick is a porous material and moisture can travel through it via capillary action, essentially the same force that draws water up through the sponge or towel. Water doesn't just travel horizontally through the brick, it moves vertically as well. This creates an inevitable problem. Rainwater will always reach the first 150 millimeters of every wall through splashback from ground. To prevent this moisture from climbing upward through the facade, Approved Document C mandates a dam-proof course, or DPC, usually in form of a membrane positioned at least at 150 millimeters above the ground level. It is a simple but critical detail, one that recognizes the fundamental behavior of moisture in porous materials. Warranty provider and HBC standards take this even further, recommending that splashback zones on terraces be executed in impermeable material entirely. The resulting detail is quite robust. In this case, it's an aluminum flashing chiseled into the first 2 courses of brick with weep holes positioned directly above. Water has very little opportunity to reach the brick surface, and therefore virtually no chance of penetrating through it. It is what we call belt and braces approach. Now here's the fascinating bit of construction industry. The industry discovered capillary effect and introduced DPC at the bottom of the brick facade in the early 19th century, quite an achievement for the time. But apparently it took another 150 years for the same industry to discover gravity. Consider this London building from 60s or 70s. It has proper damper, of course, and weep holes at slab level, and it works perfectly, no visible stains. The designers clearly understood that water could travel upward through masonry walls via capillary action. But look at the parapet. The staining isn't at the bottom, it's at the top, where the brick is completely covered in moss. There is so much vegetation growing on the surface that it resembles a true green facade. The designers probably assumed that the capillary effect works only upward to negate the effect of gravity. But I was told that neither the gravity nor capillary effect work like that. Capillary effect works downwards too. So if you are using any porous materials, brick, stone, insulated render, you need to protect the wall with a coping. That includes a proper drip detail. Approved Document C now includes a comprehensive diagram showing exactly this. It details the provision for coping on the top of the parapet with drip details at the edges. And importantly, it prescribes a damp-proof course below the coping, especially when the coping itself is made from porous material. Warranty providers take this guidance significantly further. LABC and NHBC specify minimum slopes and require the drip detail to project at least 40 to 50 millimeters or 2 inches away from the wall, depending on the coping geometry. LABC go one step beyond, prescribing specific overlap requirements for damp-proof coarse membrane below porous coping. Now here's what happens when you ignore this guidance. This example shows precast concrete coping with no projection whatsoever, actually sloped inwards towards the brick wall. As a result, we can see water ingress, hopefully just externally, forming at the location where the slope meets the wall. Some facade engineers, myself including, believe that porous materials like concrete or stone simply shouldn't be used on horizontal surfaces at all, or at the very least, they require comprehensive protection. But why might a 25mm protrusion be insufficient for brick details? Or why is zero protrusion coping completely inappropriate? The answer lies in the construction tolerances. In situ construction is inherently imprecise, and brickwork is particularly challenging in this regard. Even the most skilled bricklayer will struggle to achieve perfectly plumb walls in all directions. This image demonstrates the problem perfectly. The window sill below each opening are identical components, yet they appear to project different distances from the facade. This is not a manufacturing defect. It is the reality of coordinating different trades. The windows are installed by glazing contractor and the brick is installed by the bricklayer, and it's never installed in a perfect straight line. So as a result, we have the sills protruding to different dimensions from all brick openings, and individual sills can vary in projection from one side of the same window to the other. This is why minimum protrusions matter. What looks adequate on paper may prove insufficient when real-world tolerances are applied. These tolerance considerations apply beyond masonry facades. NHBC standards specifically prescribe drip details above insulated render systems for precisely the same reasons. Looking at this example, the importance becomes immediately apparent. Insulated render facades without proper drip details above them simply do not survive the facade warranty period in Britain. A capping with integrated drip details isn't optional, it's absolutely essential. Since we are examining this particular building, it presents an excellent opportunity to discuss modern-day gargoyles. We cover balconies and terrace drainage extensively in our other courses, but this building demonstrates how these elements directly impact facade design strategy. Notice that these balconies are positively drained, meaning that there is a deliberate slope directing water to gutters that connect to rainwater pipes. For this type of balcony systems, warranty providers like NHBC require overflow mechanisms as standard practice. But here is the crucial distinction. An overflow pipe serves as a warning system, indicating that the primary drainage has become blocked and water is ponding beneath the balcony decking. It signals that gutter maintenance is urgently needed. The overflow is a diagnostic tool, not a backup drainage strategy. Unfortunately, this distinction is not widely understood, and in many buildings, the overflow mechanism ends up functioning as a primary drainage strategy for most of its operational life. My preferred approach is to direct the overflow pipe through the balcony slab onto the balcony below, as demonstrated in our interactive detail. In this case, if the drainage is compromised, the neighbors below will notify the occupants of the apartment above about the blockage, and the blockage will be dealt with promptly, not to cause any further nuisance. Which, to be fair, exactly what happened in this instance. However, the notification came too late. The drainage blockage had already caused damage to the facade and the balcony balustrade below, requiring comprehensive cleaning and repainting. If, however, overflow pipes must be directed externally through the facade or the balustrade, it is recommended to treat them as modern-day gargoyles, adopting a minimum dimension of 30 mm in accordance with LABC balcony edge clearance detail. This brings us to the ongoing tension in facade design. There is a constant tug of war between architects and facade engineers over water defense features. Architects tend to prefer sleek, minimalist facade without any protrusions below the windows or above parapets, achieving those seamless surfaces. The current architectural culture celebrates successfully deviating from building regulations as design achievement, a demonstration of sophisticated, good detailing. Consider this brick facade in London. The brick reveals don't cover the window frames as building regulation guidance would typically recommend. Instead, the windows sit completely flush with the brick surface. There is no visible protruding window sills whatsoever. No movement joints, no rainwater pipes, no gutters, no damp-proof courses, and certainly no visible weep holes. So does this mean that the building fails to comply with building regulations? Actually, no. This building only appears to be traditional masonry construction with punched window openings. In reality, it's something quite different. A precast concrete facade with curtain wall glazing. The curtain wall system overlaps concrete with weather seal membrane at the back of the precast concrete columns and beams. This allows the glazing to sit flush with the surface without compromising weather performance. There's no cavity behind the brickwork, which explains the absence of cavity trays and weep holes that would normally appear every other brick. The bricks themselves are cast into the outer surface of the concrete and serve purely decorative purpose. They are essentially architectural texture rather than functional masonry. Because the system isn't classified as cavity masonry wall, designers weren't required to follow approved document C guidance on parapet copings and related details. But here's the thing, rainwater doesn't read building regulations. It stubbornly follows the laws of physics instead. We'll probably need another couple of decades of gravity and capillary action working their relentless magic before building regulations catch up and close this particular loophole for the architects to explore. While we are on the topic of the precast concrete facades, we find ourselves in a situation where neither building regulations nor warranty providers' standards provide adequate guidance and best practice detailing in water management. With these facade types, we rely on British Standard Institution, or BSI, guidance, commonly known as British Standards. British Standard guidance specifies two-stage seal joint between precast concrete elements, with the inner seal positioned behind the line of the porous facing element, which is essentially a fancy name for brick slips. As you'll recall from Professor Straub's lecture, the chamber between these two sills requires drainage through weep holes in either vertical joints, horizontal joints, or both. We have included a comprehensive interactive 3D model as part of this course to demonstrate these principles in details. For complex precast concrete assemblies, weep holes may even be required at corners where multiple panels meet. Check out our retrofitting course for more information on this detail. Regarding curtain wall screens, building regulations don't provide detailed design strategies or specific guidance for drainage and weep hole placement. This responsibility falls to industry best practice and manufacturer systems details. We have included an interactive 3D detail with annotations explaining how various curtain wall manufacturers typically address these requirements. This strategy closely parallels precast concrete facades. It is a two-stage seal system, but rubber gaskets replace silicon sealants. The outer seal forms between the pressure plate and the glass, while the inner seal develops between the mullion or transom and the inner face of the glazing unit. The gap between the two seals is drained through deliberate cuts in the outer seal gasket. NHBC standards provide excellent diagrams detailing the interface between curtain wall facades and other facade elements. These details offer crucial guidance for proper installation. The key principle is positioning the weather seal membrane behind the inner seal gasket at the bottom at both jamb and base details. A common installation error involves inserting the weather seal membrane between the mullion or transom and the inner face of the glazing unit. This approach is both cheaper and easier to install, which explains its frequent occurrence. However, this shortcut creates significant risk. Water can migrate from the drained gap to the behind of the weather seal interface, potentially entering the building interior. The head detail requires different treatment. NHBC guidance recommends attaching the membrane in front of the outer seal, ensuring the water cannot penetrate the drained gap between the curtain wall's two seals. Also notice the membrane loop detail where the curtain wall connects to the slab via slotted connections. This accommodates slab deflection movement while maintaining seal integrity as the building responds to loads. This highlights an important point covered in our dedicated course on movement intolerances in facades. The most common defect from building movement isn't structural failure. It is air and water leakage through compromised seals. Seal performance must be considered during movement intolerance analysis for any project, and the movement intolerance analysis should be prepared by the facade engineer and not only by project structural engineer. Now let's talk about the cavities in various types of facades. Professor Straub has conducted extensive research into cavity sizing for effective drainage performance. His findings demonstrate that gaps as small as 6 to 15 millimeters can drain water effectively. The only reason we design larger cavities is to accommodate fabrication and installation tolerances, ensuring we achieve that minimum effective gap even when workmanship standards vary. This principle applies to drainage slot design in base details and head reveal flashings. Perforations as small as 6 millimeters by 25 millimeters can provide sufficient drainage while remaining small enough to prevent vermin infestation. However, Approved Document C and British warranty provider standards specify significantly larger cavities based on project location and exposure conditions. NHBC standards require cavities in masonry veneer facades up to 75 mm wide in very severe wind-driven rain exposure locations. NHBC standards also differentiate cavity requirements based on the cladding joint types. Cladding with open joints require a minimum 50 mm cavity, while baffle, labyrinth, or rebated joints cladding can accommodate slightly smaller 38 mm cavities. A very random dimension, nobody knows where it came from, and I will not pretend to know the logic behind this rule. In his lecture, Professor Straub correctly pointed out that cavities also present fire risks. Fire can spread within the cavities through chimney effect much more rapidly than across external surfaces. Cavities require proper compartmentalization. We have a dedicated course on the fire safety in facades that explores barrier placement and performance in detail, and it is available on Facade Intelligence. But there is an important rainwater management issue with closed-state cavity barriers that's worth highlighting. Closed-state mineral wool vertical barriers work perfectly fine with impermeable materials like aluminum cladding, especially when the mineral wool sits directly against the back of the cladding panel. With brick, however, we encounter our old friend, capillary effect again. Water travels not just vertically through brick, but laterally as well. And this is exactly why we create cavities behind brickwork in the first place. The problem arises when closed-state cavity barriers make direct contact with the back of wet brickwork. Once the brick becomes saturated, water migrates through the brick onto the mineral wool surface of the cavity barrier. The barrier gets wet and transfers moisture deeper into the wall assembly. Even worse, prolonged moisture exposure can cause the barrier to deteriorate, potentially compromising its fire performance precisely when you need it most. The warranty providers are well aware of this issue. Their standards specifically require the barriers to be separated from the brick by a damp-proof coarse membrane to prevent moisture absorption. However, I'm told this detail is frequently missed during the installation. The rubber is combustible material, and designers and installers see a rubber membrane as an inappropriate element of the fire barrier. But here is a crucial point. Simply following the prescriptive requirements of building regulations isn't what matters most. What's truly important is understanding the reasons behind the guidance. The rationale is virtually never explained. We are told what to do, but rarely why. Understanding the logic behind best practice details is essential. This is precisely why we have included Professor Straub's lectures in this course. He explains underlying concepts rather than simply prescribing solutions, a far more valuable approach than merely reciting regulatory requirements. Mindless application of building regulations can create more problems than it solves. So we want to recommend further reading on this topic. These two books, Moisture Control for Residential Buildings by Joseph Stibrick, and of course, High Performance Envelopes by John Straub. I cannot recommend them enough. Also check the publications and research papers on the Building Science Corporation website. Obviously, all models and drawings from this course are available on the Facade Intelligence platform. Please consider becoming a member of Facade Intelligence if you haven't done so already. And most of the concepts presented in this course are covered in more detail in dedicated courses and qualifications provided by the Institute for Architectural Science and Technology. The next part of the course are the practice multiple choice questions relevant to the topic, where we will introduce even more concepts related to the topic. Please do not skip them before taking the final exam and obtaining your certificate of completion. Thank you for joining Professor Straub and me on this journey through rainwater management in facade design. Understanding these principles will serve you well in creating facades that successfully manage Britain's challenging climate.